Visual, a sleepy spacecraft. Instead of a small blue flame, a miniature sun erupts behind it. The screen floods with white light. Narrator, calm, almost amused. Nuclear rockets. They sound easy, don't they? We split the atom. We power cities. We build submarines that circle the planet underwater for months without refueling. So why not strap a reactor to a rocket and go to Mars in a few weeks? I mean, come on. Chemical rockets burn glorified fire. Nuclear rockets use the energy that powers stars. It feels obvious. Almost embarrassing that we're not already doing it. And yet, every time we seriously try, physics shows up like an uninvited guest and says, slow down. And this is where Richard Feynman would smile. Because the problem isn't engineering. The problem isn't that the universe has rules, and nuclear rockets run straight into them. Let's start with the dream. A conventional rocket burns fuel and oxidizer. The hot gases expand and blast out the back. Newton's third law, push stuff backward, you go forward. That's it. But chemical bonds? They're tiny energy differences between electrons. They're cute. They're weak. Nuclear reactions, that's rearranging the nucleus itself. Millions of times more energy per kilogram. So the naive calculation goes like this. If nuclear fuel has millions of times more energy, shouldn't my rocket go millions of times faster? Bold, maybe even arrogant. But physics doesn't care how bold you are. Let me introduce you to the quiet tyrant of spaceflight, the rocket equation. It looks innocent, just a little logarithm, but it rules everything. Your change in velocity, your ability to go somewhere, depends on two things. 1, how fast you can throw propellant out the back. 2, how much propellant you're willing to carry. That's it. Not how energetic your fuel is in some abstract sense. Not how futuristic your reactor looks. What matters is exhaust velocity, how fast you throw mass backward. Because here's the catch, and this is the first place physics smirks at us. Energy is not thrust. You can have enormous energy, and to fast-moving mass, you're not going anywhere. Imagine you're floating in space on an office chair. You want to move forward, so you throw tennis balls backward. Each throw gives you a little kick. Now imagine instead of tennis balls, you throw bowling balls. Heavier, more push. Now imagine you could somehow throw them at 10 times the speed. That's the key. Not how much chemical energy was used to make the ball, not how hot your muscles feel. What matters is momentum. Mass times velocity. Rockets don't ride on energy, they ride on momentum. Now here's where nuclear rockets get interesting. In a nuclear thermal rocket, you don't explode bombs behind you. That would be dramatic. Instead, you use a reactor to heat hydrogen gas to absurd temperatures, thousands of degrees. The hydrogen expands and blasts out the nozzle. Because hydrogen is so light, it can achieve very high exhaust velocity. That's good. Much better than chemical rockets. In theory, you could cut travel time to Mars nearly in half. So why aren't we already there? Why did projects like NERVA in the 1960s stall? Because physics has more layers. Let's go microscopic. Inside a nuclear reactor, uranium atoms split. When a uranium-235 nucleus absorbs a neutron, it becomes unstable and splits into 2 smaller nuclei, releasing more neutrons and a lot of energy. That energy appears as kinetic energy of fragments and gamma radiation. On the atomic level, it's violent. Tiny fragments slam into surrounding material, heating it. That heat transfers to hydrogen gas. Hydrogen molecules vibrate faster and faster. Temperature is just the average kinetic energy of atoms. Hotter means faster motion. Faster motion means faster exhaust. But here's the problem. Materials exist, and materials melt. You can't heat hydrogen arbitrarily high because your reactor core is made of something. And that something has atomic bonds. Those bonds can only withstand so much vibration before they break. Melting is not a suggestion. It's what happens when atomic vibrations overwhelm bonding forces. So your maximum exhaust velocity is limited not by nuclear energy potential, which is enormous, but by the melting point of your materials. The universe isn't stopping you because nuclear energy is weak. It's stopping you because matter itself has limits. Let me give you an analogy. Imagine you have the world's most powerful stove. Infinitely powerful. You put a pot of water on it. Can you heat the water to 10 million degrees? No, because the pot melts first. The limiting factor isn't your energy source, it's the container. And in a nuclear rocket, the reactor is the pot. Now let's talk about another uncomfortable detail. Radiation. The nuclear reactor doesn't just produce heat, it produces neutrons and gamma rays. These are not polite particles. They don't politely stay in the core. They scatter. They penetrate. They break molecular bonds. They damage materials. They scramble electronics. And if you're planning to put humans on top of this thing, they are not fans of neutron flux. So now you need shielding. Shielding means mass. Mass means more propellant. More propellant means diminishing returns because of the rocket equation. The equation always comes back like entropy, like death, like taxes. And this brings us to something deeper. The second law of thermodynamics, entropy always increases. Energy spreads out. Heat flows from hot to cold. In a reactor, you're trying to create extreme order, controlled fission, controlled heat transfer, directed exhaust. But radiation leaks, heat leaks, materials degrade. Over time, the reactor becomes less efficient. Microscopically, atoms are being displaced. Lattice structures are damaged. On the atomic scale, it's chaos. On the macroscopic scale, it's maintenance nightmares. This is the micro versus macro story. At the micro level, the laws are simple. Neutrons collide, atoms split, bonds vibrate. At the macro level, you get cracked fuel rods, warped nozzles, and brittled metals. The universe doesn't hate nuclear rockets. It just applies the same rules it applies to everything. And those rules accumulate. Now someone will say, fine, just build better materials. Sure, let's think that through. Stronger materials mean stronger atomic bonds. Stronger bonds usually mean higher melting points. But stronger bonds also mean less flexibility, more brittleness, more susceptibility to radiation damage. Everything is a trade-off. Physics is the art of trade-offs. There is no free lunch. You can't escape conservation of energy. You can't escape conservation of momentum. And you definitely can't escape entropy. Let's push the idea further. What if we skip heating hydrogen? What if we use the nuclear reaction products themselves as exhaust? Now we're talking nuclear pulse propulsion. Tiny bombs detonated behind a spacecraft. That would give you enormous exhaust velocity. In fact, absurdly high. Projects like Orion explored this seriously. And in pure physics terms, it works. Momentum from nuclear explosions pushing on a giant shock absorber plate. Simple, brutal, effective. So why didn't we build it? Because physics is not the only constraint. We live on Earth. Earth has an atmosphere. Radioactive fallout spreads. Treaties exist. Societies X's. T. And here's something profound. The laws of physics allow certain things, but the conditions of reality make them untenable. The universe says yes, but let me ask you something. Have you ever noticed how often our grandest dreams run into invisible walls, faster than light travel? Relativity says no. Perpetual motion machines, thermodynamics says no. Infinite energy, conservation laws say no. And nuclear rockets, they don't violate physics. They just run up against its fine print, the details. And the details are where reality lives. There's a deeper lesson here. When you first hear nuclear rocket, your brain imagines limitless power. Because in everyday life, more energy solves problems. Stronger engine, go faster. Bigger battery, last longer. But at cosmic scales, more energy creates new problems. More heat, more radiation, more structural stress. Power amplifies constraints. It doesn't erase them. Think of it like turning up the volume on a speaker. At low volume, everything sounds fine. Turn it up too high, the cone tears. The electronics overheat. The system fails. The music wasn't the problem. The amplitude was. Nuclear rockets are turning the cosmic volume knob to 11, and materials scream. Now here's the philosophical pivot. You might feel disappointed, like the universe is holding us back. But I want you to look at it differently. The fact that there are limits is the reason anything stable exists at all. If atomic bonds were infinitely strong, chemistry wouldn't work. If they were infinitely weak, matter would dissolve. If entropy didn't increase, time wouldn't have direction. If conservation laws didn't hold, reality would be chaos. The same rules that limit our rockets allow stars to burn steadily for billions of years, allow planets to form, allow DNA to persist long enough for you to exist. Limitation. S are not bugs, they are structure. On the microscopic scale, every atom in a reactor obeys quantum mechanics blindly. Neutrons don't care about Mars. Hydrogen doesn't care about astronauts. Atoms follow probability distributions. Wave functions evolve. That's it. But on the macroscopic scale, we see ambition, dreams, civilizations trying to cross the void. This contrast is astonishing. The micro world is meaningful. And yet they are the same world. Your desire to reach Mars is encoded in atoms that obey the same physics that melts reactor cores. That's the unity of nature. Richard Feynman once said that nature cannot be fooled, and that's the warning. You can't market your way past the melting point of carbon. You can't negotiate with neutron cross-sections. You can't inspire entropy into decreasing. The laws are not suggestions. They are the script. We are actors improvising within it. But here's the beautiful part. Within those constraints, nuclear rockets might still work. Carefully designed reactors, advanced ceramics, shadow shields to protect crews, perhaps robotic missions first. Physics doesn't say never. It says, pay the cost. And the cost is engineering complexity, mass, safety systems, redundancy. It's humility. Humility is underrated in technological optimism. We love breakthroughs. We love the idea that one genius idea will unlock the stars. But more often, progress is a negotiation with reality. A long conversation with the laws of thermodynamics, a patient refinement of materials science, an acceptance that every gain introduces new weaknesses, and maybe that's fitting, because life itself is like that. You are a temporary island of order in a universe trending toward disorder. Your body constantly burns energy to maintain structure. Stop eating, stop breathing. Entropy wins. You are not a closed system. Neither is a rocket. Neither is civilization. Everything complex survives by exporting entropy elsewhere. A nuclear rocket exports entropy violently in hot hydrogen and radiation, and it must survive its own internal chaos long enough to matter. We are made of the same nuclear processes we want to harness. The carbon in your cells was forged in stars. Stars are giant nuclear reactors contained by gravity. Why don't they melt? Because gravity provides confinement on a scale we cannot replicate. Pressure balances heat. Fusion balances collapse. A star is a negotiation between forces. Our rockets are tiny imitations of stellar processes. But we don't have stellar gravity. We have metal tubes. And metal has limits. So when someone says, why don't we just use nuclear rockets and solve space travel, you can smile, not condescendingly, but knowingly, because you understand that just is doing a lot of work in that sentence. You understand that energy is not momentum, that temperature is atomic vibration, that materials are bound by quantum mechanics, that entropy always collects its fee. You understand that the universe is subtle. And here's the final twist. The fact that it's hard makes it meaningful. If crossing the solar system were easy, it wouldn't require cooperation, ingenuity, patience. It wouldn't reveal the depth of physical law. Difficulty is what turns engineering into art. Constraint is what turns survival into triumph. The melting point of graphite, the half-life of uranium, the cross-section of a neutron. These are not obstacles placed by a cruel universe. They are the texture of reality. And we are learning to navigate that texture. One day, perhaps, a nuclear thermal rocket will leave Earth orbit. Hydrogen blazing invisibly, crew shielded behind layers of engineered matter, every bolt C, calculated against radiation damage, every component designed with respect for entropy, not defying physics, but dancing with it. And when that happens, it won't be because nuclear rockets were easy. It will be because we listened when physics showed up, because we accepted Feynman's warning that nature cannot be fooled, only understood. So let me leave you with this. If the universe has such strict laws, if entropy always rises, if materials always melt, why does complexity exist at all? Why are you here, able to question melting points and neutron flux? Why does the universe permit temporary islands of order that dream of escaping their cradle? Maybe the laws aren't barriers. Maybe they are the reason there's a story at all. A story where atoms assemble into minds, where minds imagine nuclear suns in metal tubes, where the same physics that limits us also empowers us. You are not separate from these laws. You are an expression of them, a local, temporary defiance of disorder, a configuration of matter that has learned to ask, why not Mars? And the universe answers patiently, here are the rules. The rest is up to you. So tell me, if we do build nuclear rockets knowing all the constraints, knowing the costs, should we, or is the greater adventure learning how to live beautifully within the limits we already have? I'll see you in the comments.